Lesson 3, Intervals, Scales, and Tuning. It's irrational. Defining and constructing a scale, or scaling the heights. Why does Western music sound different from Chinese music? The musical scales are different. Different choices were made about which notes in an octave to use. Imagine an ancient Chinese musician playing a note, C, on a stretched string. Divide the string into 3 parts, and the string will play a G. That sounded good with the C. Divide again into 3 parts, and a D is the result. It also sounded good with the G and the C. Repeat, starting from the D, to get the A. Repeat again, and get an E. But repeat one more time, and the result is a B, which doesn't sound good when played with the original C, even though the B is close to C. So a 5-note scale, C, G, D, A, E, became the basis for Chinese music. It is called a pentatonic scale. Penta meaning 5. But we haven't yet defined the word scale. It is a range of notes covering an octave from one frequency to a frequency twice as big, such as from an A 440 Hz to A 880 Hz. Our standard Western scale is called heptatonic because it is a 7-note or 7-step scale, even though we play the 8th note at the top end to complete the octave. Musicians also call it the diatonic scale and know that it comes in 2 versions, major and minor. But the scale really has 12 notes called half steps. We call this the chromatic scale. Certainly, it has a lot of color, as the word chromatic from chromos indicates. An interval is the distance in pitch between 2 notes. For example, an octave is the distance between a starting note called a fundamental and 8 notes higher, while a fifth is the distance between a fundamental and the 5th note on the major scale. We call the latter a perfect fifth. It really does sound perfect. Nearly every musical tradition in the world uses scales with the 5th in the octave because they are the 2nd and 3rd overtones or harmonics when we hear a single note being produced by a vibrating string or column of air. The exception is Javanese or Indonesian gamelan music. A gamelan makes music with vibrating bars, which have different vibration patterns. So their scales are not based on harmonic overtones, and they don't have an interval of a 5th. We know that to make an octave, we simply double the starting frequency. Taking 3 halves of the starting frequency makes a 5th. But that's the easy part. How could we construct the rest of a simple scale, such as the pentatonic? There are complications. To make the calculations easy, let's start with a 100 Hz note, which is roughly a low G, about the pitch of my speaking voice. An octave above would be 200 Hz. If we build a 5-note scale by splitting up the distance into equal increments of 20 Hz, using 100, 200, or 100, 120, 140, 160, 180, and 200, the resulting scale will sound non-standard. Go up another octave to 400 Hz. If we go from 200 to 400, again by 20 Hz at a time, we would have a 10-note scale. The notes would sound much closer together. Going up another octave, 20 Hz at a time, from 400 to 800 Hz, would lead to a 20-note scale. This means sopranos would have more notes available in their octaves than tenors or basses. This is an illustration of the challenge that I mentioned in the previous lesson, trying to reconcile addition and multiplication. Overtones have additive frequencies, but intervals and scales are multiplicative. Instead of adding the same number each time, such as 20 Hz, we should multiply by the same number each time. That way, we'll figure out where to put the notes in a single octave. And then we'll use multiplication, either multiplying or dividing by 2, to get the same notes in higher octaves for sopranos and lower octaves for basses. For example, let's start at 100 Hz. That's my baritone's G, and go to 200 hertz, which is a G an octave higher. The multiplication approach means that a perfect fifth would be 3/2 of 100, or 150 hertz. It's halfway up the octave in frequency, but not halfway up in distance. It's 5/8 of the way. For tenors starting at 200 hertz, 3/2 of 200 would be 300 hertz. The baritone's fifth goes up 50 hertz, but the tenor's fifth goes up 100 hertz. Multiplication is the solution here. There's nothing more to add. In fact, there is more to add. Constructing the rest of the scale, that is, the other notes in the octave, is called tuning. And it's more than just what musicians do to prepare to play. It's about how to space out the notes in a sensible, logical, and reliable way. And it took over 2,000 years to evolve. The evolution of tuning led to an evolution in composition. So let's talk about tuning. Tune in, don't tune out. The first approach is called just tuning. Just tuning doesn't mean only tuning, it means fair tuning. The idea is to start with the fundamental and then use the overtones, but then move notes up or down into the correct octave by multiplying or dividing the frequency by 2. But there's a problem. Mathematically, it doesn't matter how many times you multiply or divide by 2, you still can't get ratios of 4/3 or 5/3 needed to get the notes in a heptatonic scale that aren't in a pentatonic one. What's the solution? Just tuning takes overtones from other notes to replace the overtones that aren't available from the fundamental. However, if we start with A, we can bring every note into tune with it, but not necessarily in tune with each other. We can't create a scale so that the overtones of one note exactly match up with the other notes. Even with only 3 notes, the additive structure of overtones conflicts with the multiplicative structure of intervals. The math tells us it's a problem with all instruments, not just pianos or fixed-tuned instruments. Now, if you only use notes played with the fundamental, you don't transpose, and you only play single notes at a time, just tuning is fine. It works for Indian sitar and tabla music, and it works for a bagpipe, since the drone drones on, and the chanter, the pipe that looks like a recorder, plays one note at a time. But transpose, change keys, or play chords, and things go awry. That leads us to approach number 2, Pythagorean tuning. Have you heard the expression, pull yourself up by your own bootstraps? It's a paradox of sorts, but it does provide another way to tune an octave. The bootstrapping idea means go from one note to the next using the overtone frequencies. Just tuning started with an A and used only the overtones of A. An alternative is to start with A to get to the next note, and then use that next note as a new reference. It's another great way to make a pentatonic scale, but it ends there. A very familiar piece that uses it is the second movement, the Largo, of Dvorak's New World Symphony. A D-flat major pentatonic scale is played by the English horn. It is the instrument in the orchestra whose sound spectrum is closest to the human voice. Carl Orff loved the pentatonic scale too. Its simplicity made it a perfect choice for children to learn. The idea is an old one, hence the name Pythagorean tuning. Pythagoreans, I mentioned Pythagoras, and about whom I'll tell you more in a moment, wanted the fifth to be exactly in tune. To do this, start from the fundamental and go up 7 half steps or 7 keys on the piano. That gets you to the 5th note of the major scale. From that new starting point, repeat the process and keep repeating. For example, starting on A, the 5th note of the A major scale is E. The 5th note on that scale is B. The next ones are F sharp and then C sharp. It's simply a case of multiplying each successive frequency by 3/2. The result is known as the circle of fifths. Pythagoreans weren't bothered by needing to tune musical instruments differently depending on which key the music was written in. The Pythagoreans worshipped mathematics and believed it was the key to understanding the universe. They loved whole numbers and fractions. They developed the philosophical concept of music of the spheres, namely, that simple proportions govern how the sun, moon, and planets move, and that also it's a form of music. Proportions are fractions or ratios, and anything that couldn't be expressed in a ratio was not rational, coming from the word ratio. It would be irrational. In many ways, the Pythagoreans were indeed irrational in the sense of being mad. And what really made them mad, in the angry sense of the word, was that neither math nor music followed their principles. Imagine a right triangle with each of the two shorter sides having length 1. Mathematics tells us that the square of the longest side, the hypotenuse, should be the sum of the squares of the other two sides. In this case, 1 squared plus 1 squared equals 2. That means the hypotenuse must be the square root of 2, a number that can't be expressed as a ratio. It is not rational, it is irrational. According to legend, when Hippasus, a follower of Pythagoras, discovered that, they drowned him for heresy. Isn't it deliciously ironic that the theorem applied here is called the Pythagorean theorem? On the face of it, Pythagorean tuning seems like a brilliant solution. But let's see what happens when we do this on a piano. The very bottom note is an A, called A0, which has a frequency of 27.5 hertz. Going up fifths, tuning them exactly by multiplying the frequencies by 3/2, will take 12 steps to get all the way to the highest A, called A7. It's called A7 because it's 7 octaves above A0. But going up 7 octaves is equivalent to doubling the frequency 7 times. With just tuning, A7 has a frequency of 3,520 hertz. With Pythagorean tuning, it's 3,568 hertz. Oops. We can't get the top A into tune with all the other fifths and with all the octaves at the same time. That explains why no piano is ever exactly in tune. The gap between 7 octaves and 12 fifths, that is between just tuning and Pythagorean tuning, is called the Pythagorean comma. It may seem small quantitatively to you, it's only about a 1% difference, but it had a huge effect on composition. And that brings us to our third attempt and beyond, tempered tuning. There's no exact solution to fixing the gap, this Pythagorean comma, only approximate ones. One option is to put the entire gap in the last fifth. Another option is to spread the gap out a bit. That way, while more of the fifths won't have perfect 3/2 ratios, at least the last one won't have such a large gap. This makes the keyboard sound good in many different keys. The idea, called tempering, helped music evolve from Baroque to Romantic. It permitted Bach to write his Well-Tempered Clavier, a collection of pieces, one in each of the 12 major and minor keys. But I wish to point out, technically, it should only be called the Pretty Well-Tempered Clavier, because it still had some weaknesses, and Bach still had to avoid certain intervals. By 1900, tuning had reached the next stage of evolution. Being well-tempered was not enough. Equal tempering or equal temperament on a piano spread out the gap evenly. Great, you say, except that it meant every fifth on a modern tune or equal tempered piano would be equally out of tune. That's because of the inequality we saw between just tuning and Pythagorean tuning. In other words, 3/2 to the 12th power is not equal to 2 to the 7th power. Mathematics comes to the rescue. Let's see what we could use instead of a ratio of 3/2 to get equality. Call that ratio R. We need a value of R so that R to the 12th power equals 2 to the 7th power. Solve for R and you get that R is 2 to the 7/12 power. That's an irrational number approximately equal to 1.4983 ... Not quite 1.5. We can look at it another way. Divide the octave into 12 equal half steps. Remember that we do this multiplicatively, not additively. Then each step should have a ratio of 2 to the 1/12th power, or approximately 1.0595. That is the 12th root of 2. Knowing this number, we can now form the entire chromatic scale. That is, multiply the frequency of an A by the number 1.0595, or if you want more precision, 1.059463. Multiply that 12 times, and we get back to an A an octave higher. Now the ratio of frequencies between any two notes is the same, and a given interval never changes wherever you play it. As an illustration to compare the tuning methods, start with the famous A440 Hz. The just C sharp is 550 Hz. The Pythagorean C sharp is approximately 556.89 Hz. And the equal tempered C sharp is about 554.36 Hz. The Pythagorean one sounds sharper and higher in pitch. Equal tempered is nicely between the just C sharp and the Pythagorean C sharp. Our ear has grown accustomed to irrational frequencies, using equal temperament in a piano spread around the world, and quickly stopped sounding out of tune. Most people have never heard any other tuning. Pythagoras would consider each note in our tuning to be slightly out of tune. We have turned the tables. We now consider Pythagorean tuning to be the one out of tune. At least we still use his triangle theorem. So why a 12-note system? Why does the equal tempered system use 12 notes and not some other number? Would another choice work better? To build a scale with equal spacing, we need the octave, the fifth, the fourth, and the major third. If the fundamental is 100 Hz, in just tuning, which does sound the best, the octave would be double the frequency at 200 Hz, and the fifth, 3/2 at 150 Hz, and the fourth, 4/3 at 133 1/3 Hz, and the major third at 5/4, 125 Hz. Those are the notes perfectly in tune with the overtones. And those fractions, 1.5, 1.33, and 1.25, are the key ones. It turns out that with 12 equally spaced notes, we include notes close to these fractions. It doesn't happen if you have fewer than 12 notes. The equation to be solved is 3/2 to the x power equals 2 to the y power. The math involved uses logarithms in base 2, but I won't show it to you here. By the way, logarithms are also the basis of measuring loudness using decibels and measuring seismic activity using the Richter scale, which is a different meaning of scale. So to improve the approximation, we would need a 41-note octave, where the 24th note would be very close to the perfect fifth. We can get closer and closer to perfect tuning, but at the cost of making an octave with many, many notes. Remember that a perfect fifth means a ratio of frequencies of 3/2. With 12 notes, 2 to the 7/12 is 1.4983. With 41 notes, 2 to the 24/41 power is 1.5000419. So close to 1.5. An imperceptible improvement, though. And if you're curious, a 665-note octave with a fifth at the 339th note would give a ratio of 1.499999902. Very close to 1.5. But that's why we stop at 12 notes in an octave. It's the best compromise, but it's still a compromise. Could you build a scale on major thirds instead of fifths? Yes, that's called mean tone temperament. The equation here to be solved would be 5/4 to the x equals 2 to the y. And mean temperament tuning did exist. Dissonance. Which notes on the 12-note system sound good together? that is, consonant, and which combinations of notes sound displeasing or discordant, that is, dissonant. As we learned earlier, for the Pythagoreans, consonant notes had ratios of frequencies with small numbers, and dissonant notes had ratios expressed with large numbers. So the ratios 3/2, 4/3, 5/4, and 6/5 correspond to a perfect fifth, perfect fourth, major third, and minor third, respectively. That's why C, E, and G chord sounds pleasant. E is 5/4 as large as C, G is 3/2 as large as C. A 5/3 ratio is a major sixth, and an 8/5 ratio is a minor sixth. But the more complicated the fraction, the less harmonious the sound. An intriguing dissonant note is called the tritone, or the devil's interval. It is one semitone lower than a fifth, such as C to F sharp or F sharp to C. F sharp is the furthest note away from C inside the octave. The ratio of the frequency is 45 to 32, or 64 to 45, depending on how it is tuned. Liszt used it to suggest hell in his Dante sonata. Richard Wagner used it in Tristan and Isolde. There is more mathematics at play here. The German mathematician and physicist Hermann von Helmholtz studied this. He used the term beats differently than we used it. He uses it for the throbbing sound produced when two notes are played slightly out of tune with each other. The speed of the beats increases as the notes get farther apart. Once they're very far apart, or if the notes are the same, the beats vanish, and we hear only one note or two separate notes. This is another job for trigonometry. Let's leave a detailed analysis of dissonance for acoustical experts. Instead, I offer a marvelous example of consonance. Aaron Copland's Fanfare for the Common Man. He uses 3 perfect intervals, the fourth, the fifth, and the octave, to perfection. Composition and the consequences of equal tuning. The evolution of tuning took over 2,000 years. Over a 400-year period from 1500 to 1900, the Pythagorean comma was spread out more and more equally. Steps along the way were tuning systems called mean tone, quarter comma mean tone, Werkmeister 3, Kernberger 3, well-tempered, quasi-equal tempered, ending finally at equal tempered. By the late 1800s, pianos were all being tuned using equal temperament. An interesting little tidbit is that there is almost no piano guitar music before 1900. That's because guitars have frets that go across all the strings. So when guitars were first made in 1500, equal tempered tuning was necessary, but the piano didn't have it yet. So the two instruments would have been out of tune with each other. Why does tuning matter? Especially since the 3 methods we discussed are all reasonably close. Before equal temperament, composers would choose keys depending on the mood they were aiming for. When the gap was not spread out, different keys sounded very different. In pre-Renaissance music, such as Gregorian chant or plainsong music, they only used a single voice. Renaissance music put 2 simple voices together and used early versions of major and minor scales. By the Baroque period, compositions used multiple voices and more complex harmonies. The Classical period introduced modulations to other keys. And by the Romantic period, composers were a little less concerned about having a tonal center. Impressionists and 20th century composers continued to break away from tradition and eventually largely abandoned the concept of tonality. With equal tempered tuning, every key sounded good. Constraints on composition, except for the self-imposed ones, disappeared. Tuning drove composition in Western classical music. And now you know the mathematics behind scales and tuning. Understanding math means understanding tuning. And now, you are tuned into